length is the distance between successive crests. The wave height is the vertical distance from the crest to the trough. Recall from our discussion of earthquakes in Chapter 7 that when a wave travels through rock, the energy of the wave is transmitted rapidly over large distances, but the rock itself moves only slightly. In a similar manner, a single water molecule in a water wave does not travel with the wave. While the wave moves horizontally, the water molecules move in small circles, called wave orbitals, as shown in Figure 16.12. That is why a ball on the ocean bobs up and down and sways back and forth as the waves pass, but it does not travel along with the waves. The circles of water movement produced as a wave passes by become smaller with depth. At a depth equal to about half the wavelength, the disturbance becomes negligible. This depth is called wave base, and it varies with the size of the waves. If you dive deep enough, you can escape wave motion from even the biggest storm waves that have a wavelength of around 500 meters and a wave base of about 250 meters. No one gets seasick in submarines, because they avoid wave motion by diving below local wave base. Ocean currents. The water in an ocean wave oscillates in circles, ending up where it started. In contrast, a current is a continuous flow of water in a particular direction. Although river currents are familiar and easily observed, early mariners did not recognize ocean currents. Surface currents, caused by wind blowing over the sea surface, flow in the upper 400 meters of the seas and involve about 10% of the water in the world's oceans. In contrast, deep-sea currents transport seawater both vertically and horizontally below a depth of 400 meters and are driven by gravity as denser water sinks and less dense water rises. Furthermore, in certain places several processes cause surface water to sink to great depths, and in other places deep water rises to the sea surface. Thus, the entire global ocean circulates continuously. Figure 16.13 shows major surface currents and deep-sea currents in the Atlantic Ocean. Surface currents in the mid-1700s. Benjamin Franklin lived in London, where he was Deputy Postmaster General for the American colonies. He noticed that mail ships took 2 weeks longer to sail from England to North America than did merchant ships. Franklin learned that the captains of the merchant ships had discovered a current flowing northward along the east coast of North America and then across the Atlantic to England. When sailing from Europe to North America, the merchant ships saved time by avoiding the current. The captains of the mail ships were unaware of this current and lost time sailing against it on their westward journeys. In 1769, Franklin and his cousin, Timothy Folger, a merchant captain, charted the current and named it the Gulf Stream. As ship traffic increased and navigators searched for the quickest routes around the globe, they discovered other ocean currents. Ocean currents have been described as rivers in the sea. The analogy is only partially correct. Ocean currents have no well-defined banks, and they carry much more water than even the largest river. The Gulf Stream is 80 kilometers wide and 650 meters deep near the east coast of Florida and moves at approximately 5 kilometers per hour, a moderate walking speed. As it moves northward and eastward, the current widens and slows. East of New York City, it is more than 500 kilometers wide and travels at less than 8 kilometers per day. Another important difference between rivers and surface currents is that rivers flow in response to gravity, whereas ocean surface currents are driven primarily by wind. When wind blows across water in a constant direction for a long time, it drags surface water along with it, forming a current. In many regions, the wind blows in the same direction throughout the year, forming currents that vary little from season to season. However, in other places, changing winds cause currents also to change direction. For example, in the Indian Ocean prevailing winds shift on a seasonal basis. When the winds shift, the ocean currents follow suit. Ocean currents profoundly affect Earth's climate. The Gulf Stream transports 1 million cubic meters of warm water northward past any point every second, warming both North America and Europe. For example, Churchill, Manitoba, is a village in the interior of Canada. It is frigid and icebound for much of the year. Polar bears regularly migrate through town. Yet it is at about the same latitude as Glasgow, Scotland, which is warmed by the Gulf Stream and therefore experiences relatively mild winters. In general, the climate in Western Europe is warmer than that at similar latitudes in other regions not heated by tropical ocean currents. Why surface currents flow in the oceans? Surface currents are driven primarily by friction between wind blowing over the sea surface and surface water. The winds simply drag the sea surface along in the same direction that the winds are blowing. In Figure 16, 16. The green arrows show the major prevailing winds over the North and South Atlantic Oceans. The orange arrows show the elliptical surface currents, called gyres, in the same regions, simplified from figure 16.13. The North Atlantic gyre circulates in a clockwise direction, and the southern gyre circulates counterclockwise. The circular motion characteristic of gyres tends to trap and accumulate floating debris, especially human garbage. First discovered in the early 1990s, the Great Pacific Garbage Patch is a region of floating garbage that has accumulated in the center of the eastern Pacific Ocean between California and Hawaii. Because the gyres move in a circular fashion, floating human garbage in the oceans tends to accumulate in the center. Although the size of the accumulation is difficult to measure and it is possible to sail directly through the garbage patch without noticing an obvious accumulation, the size of the Great Pacific Garbage Patch is estimated to be about twice the size of Texas. Similar but smaller floating garbage patches exist in the western Pacific and North Atlantic. Although the name conjures up images of a floating garbage heap, these gyre-produced concentrations of garbage consists mostly of small pieces of floating or suspended plastic. Most commonly used plastics do not decompose in the ocean but rather break down into smaller and smaller pieces. This microplastic debris is mixed and moved about by wave and wind energy and disperses over huge surface areas throughout the upper part of the ocean while also mixing with ocean water below the surface. At present, scientists understand very little about the effects these dispersing pieces of plastic have on the ocean ecosystem. Notice that the currents do not flow in exactly the same directions as the prevailing winds. Instead, the east-west surface currents in the northern hemisphere are deflected to the right of the winds. Where their flow is blocked by a continent, the currents veer clockwise to continue their circuit. In the southern hemisphere, the currents are deflected to the left of the winds and turn counterclockwise when they encounter land. These differences between prevailing wind directions and the flow directions of the surface currents suggest that forces other than wind also affect the great gyres. One force that deflects the gyres away from the prevailing winds is the Coriolis effect, named for Gaspard Gustave de Coriolis, the 19th-century French scientist who described it. To understand this effect, consider the rotating Earth. The circumference of Earth is greatest at the equator and decreases to zero at the poles. But all parts of the planet make one complete rotation every day. Therefore, a point on the equator must travel farther and faster than any point closer to the poles. At the equator, all objects move eastward with a velocity of about 1,600 km per hour. At the poles there is no eastward movement at all and the velocity is 0 km per hour. Now imagine a rocket fired from the equator toward the North Pole. Before it was launched, it was traveling eastward at 1,600 km per hour with the rotating Earth. As it takes off, it is moving eastward at 1,600 km per hour and northward at its launch speed. As it moves north from the equator, it is still traveling eastward at 1,600 km per hour, but points on Earth beneath it move eastward at a slower and slower speed as the rocket approaches the pole. As a result, the rocket curves toward the east, or the right. In a similar manner, a mass of water or air deflects in an easterly direction as it moves north from the equator, as shown in figure 16.18a. Conversely, consider an ocean current flowing southward from the Arctic Ocean toward the equator. Since it started near the North Pole, this water moves more slowly to the east than Earth's surface near the equator, and therefore the current veers toward the west, or to the right, as shown in figure 16.18b. Thus, north-south currents always veer to the right in the northern hemisphere. In the southern hemisphere, currents turn toward the left for the same reason. At the sea surface, both the prevailing winds and the Coriolis effect affect current directions. However, below the surface, the water doesn't feel the wind, it feels only the movement of water directly above. The Coriolis effect is as strong at depth as it is at the sea surface. As a result, each successively deeper layer is less affected by the wind and more affected by the Coriolis effect. Consequently, deeper layers of water in the surface currents are deflected even more to the right in the northern hemisphere, and to the left in the southern hemisphere, than is the shallowest water. The net effect of this process on the flow directions of the gyres extends down to a depth of about 100 meters and is called Ekman transport, after van Wafford Ekman, the Swedish scientist who developed the mathematics that describes the process. Deep sea currents wind does not affect the ocean depths, and oceanographers once thought, therefore, that water of the deep ocean was almost motionless and the seafloor topography changed little over time as a result. In her 1951 book, The Sea Around Us, Rachel Carson wrote that the ocean depths are a place where change comes slowly, if at all. However, in 1962, ripples and small dunes were photographed on the floor of the North Atlantic. Because flowing water forms these features, the photographs demonstrated that water must be moving in the ocean depths. More recently, oceanographers have measured deep-sea currents directly with flow meters and photographed moving sand and mud with underwater video cameras. Wind drives surface currents, but deep-sea currents are driven by differences in water density. Dense water sinks and flows horizontally along the seafloor, forming a deep-sea current. Two factors cause water to become dense and sink: decreasing temperature and increasing salinity. The global deep-sea circulation shown in figures 16.18 and 16.19 is caused by these two factors and is called thermo-aligned circulation. Recall that water is most dense when it is cold, close to freezing. Therefore, as tropical surface water moves poleward and cools, it becomes denser and sinks. In addition, water density increases as salinity increases. So water sinks when it becomes salter. Seawater can become salter if surface water evaporates. Polar seas also become salter when the surface freezes, because salt does not become incorporated into the ice. Thus, Arctic and Antarctic water is dense because the water is both cold and salty. In contrast, addition of freshwater makes seawater less salty and less dense. This effect is pronounced in enclosed bays with abundant, inflowing fresh river water and also in the polar regions when icebergs float into the ocean and melt. As we will see in Chapter 21, recent rapid melting of Greenland glaciers has introduced enough freshwater into the North Atlantic to reduce the density of surface water and alter its buoyancy. Figure 16.15 shows that the Gulf Stream originates in the subtropics. When this water reaches the northern part of the Atlantic Ocean near the tip of Greenland, it is cool and salty enough to sink. When the sinking water reaches the seafloor, it is deflected southward to form the North Atlantic deep water, which flows along the seafloor all the way to Antarctica. An individual water molecule that sinks near Greenland may travel for 500 to 2,000 years before resurfacing half a world away in the South Polar Sea. Upwelling: if water sinks in some places, it must rise in others to maintain mass balance. This upward flow of water is called upwelling. Upwelling carries cold water from the ocean depths to the surface. Upwelling also brings nutrients from the deep ocean to the surface, creating rich fisheries along the coasts of California and Peru. Several processes can cause upwelling, both in the open oceans and along coastlines. In Figure 16.15, note that the California current flows southward along the coast of California. In the southern hemisphere, the Humboldt current moves northward along the west coast of South America. Both currents are deflected westward, away from shore, by the Coriolis effect modified by Ekman transport. As these surface currents veer away from shore, water from the ocean depths rises toward the surface along the California coast and the west coast of South America. In August, water in the mid-Atlantic coast of the United States is warmed by the Gulf Stream and may be a comfortable 21 degrees Celsius. However, at the same latitude on the central California coast, the cool California current combines with the upwelling deep water to produce water that is only 15 degrees Celsius, and surfers and swimmers must wear wetsuits to stay in the water for long. The frictional drag of a prevailing offshore wind can pull surface water away from a coast. Deep water then upwells along the edge of the continental shelf to replace the surface water flowing away from shore. Winds blowing parallel to shore can also create upwelling. The wind causes water to flow parallel to shore, but the Coriolis effect and Ekman transport deflect the current, driving it away from the coast. Deep water then rises to replace the surface water. In most years, an offshore wind drives surface water away from the coast of Peru and adjacent portions of western South America, creating a strong, nutrient-rich upwelling current that produces rich fisheries along that coast. However, about every 3 to 7 years, in El Niño years, the offshore wind weakens and the upwelling does not occur or is much reduced in magnitude. As a result, unusually warm, nutrient-poor water accumulates along the west coast of South America, displacing the cold Humboldt current. El Niño's effects last for about a year before conditions return to normal. Many meteorologists now think that El Niño affects weather patterns for nearly 3/4 of Earth. The causes and effects of El Niño are described in Chapter 19. Figure 16.15 shows that the south equatorial currents of both the Atlantic and Pacific flow near the equator. Although the Coriolis effect is weak near the equator, in the open oceans, water in equatorial currents is deflected poleward. As equatorial surface water moves toward each pole, it diverges, causing deeper, colder water to rise and replace the surface water in what is called equatorial upwelling. The seacoast. As we mentioned in the introduction to this chapter, coastlines are among the most geologically active zones on Earth, where atmosphere, geosphere, hydrosphere, and biosphere all affect the local environments. Subduction occurs along many continental coasts. Waves and currents weather, erode, transport, and deposit sediment continuously on all coastlines. In addition, the shallow waters of continental shelves are among the most productive biological ecosystems on Earth. Many organisms that live in these regions build hard shells or skeletons of calcium carbonate. If they do not disintegrate following the organism's death, the remains of these shells and skeletons can become incorporated into mudstone, sandstone, or limestone as clasts. Thus, living organisms become part of the rock cycle. Weathering and erosion on the seacoast. Waves batter most coastlines. If you walk down to the shore, you can watch turbulent water carry sand grains or even small cobbles along the beach. Even on a calm day, waves steepen as they approach shoreline, crash in the surf zone, and wash up against the beach. When a wave enters water shallower than its wave base, the bottom of the wave drags against the seafloor. This drag compresses the circular motion of the lowermost wave orbitals into ellipses and slows down the lower part of the wave. At first, the incoming wave simply builds upward from a swell to a wave as the continually shallowing bottom causes the incoming water to bunch up, forcing the surface of the wave upward. Eventually, however, the bottom of the wave becomes so deformed by drag and the upper part of the growing wave gets so far ahead of the lower part that the wave collapses forward, or breaks. Chaotic, turbulent waves breaking along a shore are called surf. Most coastal erosion occurs during intense storms because storm waves are much larger and more energetic than normal waves. A 6-meter high wave strikes shore with 40 times the force of a 1.5-meter high wave. A giant 10-meter high storm wave strikes a 10-meter wide seawall with 4 times the thrust energy of the 3 main orbiter engines of a space shuttle. Seawater weathers and erodes coastlines by hydraulic action, abrasion, solution, and salt cracking, processes that are familiar from our earlier discussions of weathering and streams. A wave striking a rocky cliff drives water into cracks or crevices in the rock, compressing air in the cracks. The air and water combine to create hydraulic forces strong enough to dislodge rock fragments or even huge boulders. Storm waves create forces as great as 25 to 30 tons per square meter. Engineers built a breakwater in Wick Bay, Scotland, of car-sized rocks weighing 80 to 100 tons each. The rocks were bound together with steel rods set in concrete, and the seawall was topped by a steel and concrete cap weighing more than 800 tons. A large storm broke the cap and scattered the rocks about the beach. The breakwater was rebuilt, reinforced, and strengthened, but a second storm destroyed this wall as well. On the Oregon coast, the impact of a storm wave tossed a 60-kilogram rock over a 25-meter high lighthouse. After sailing over the lighthouse, it crashed through the roof of the keeper's cottage, startling the inhabitants. While images of flying boulders are spectacular, most wave erosion occurs gradually, by abrasion. Water is too soft to abrade rock, but waves carry large quantities of silt, sand, and gravel. Breaking waves roll this sediment back and forth over bedrock, acting like liquid sandpaper, eroding the rock. At the same time, smaller cobbles are abraded as they roll back and forth in the surf zone. Seawater slowly dissolves rock and carries ions in solution. Salt water also soaks into bedrock. When the water evaporates, the growing salt crystals pry the rock apart. Sediment transport along coastlines. Most waves approach the shore at an angle rather than head-on. When this happens, one end of the wave encounters shallow water and slows down, while the rest of the wave is still in deeper water and continues to advance at a relatively faster speed. As a result, the wave bends. This effect is called refraction. Consider the analogy of a sled gliding down a snowy hill onto a cleared, paved pathway. If the sled hits the paved surface at an angle, one runner will reach it before the other. The runner that hits the pavement first slows down, while the other, which is still on the snow, continues to travel rapidly. As a result, the sled turns abruptly. As waves approach an irregular coast, they reach the headlands first, breaking against the point and eroding it. The waves then refract around the headland and travel parallel to its sides. Surfers seek such refracted waves because these waves move nearly parallel to the coast and therefore travel for a long distance before breaking. For example, the classic big wave Mecca at Waimea Bay of Oahu, Hawaii, forms along a point of land that juts into the sea. Waves build when they strike an offshore coral reef, then refract along the point and charge into the bay. Refracted waves transport sand and other sediment toward the interior of a bay. As the headlands erode and the interiors of bays fill with sand, an irregular coastline eventually smooths out. When waves strike the coast at an angle, they form a longshore current that flows parallel to the shore. Longshore currents involve water from the surf zone and a little further offshore and may travel for tens or even hundreds of kilometers parallel to the coastline. They transport sand for great distances. Longshore sediment transport also occurs by beach drift. If a wave strikes the beach obliquely, it pushes sand up and along the beach in the direction that the wave is traveling. When water recedes, the sand flows straight down the beach, as shown in Figure 16.24. Thus, at the end of one complete wave cycle, the sand has moved a short distance parallel to the shoreline. The next wave transports the sand a little farther, and so on. Over time, sediment can move many kilometers down a coastline in this manner. Longshore currents and beach drift work together to transport and deposit huge amounts of sand along a coast. Much of the sand found at Cape Hatteras, North Carolina, originated hundreds of kilometers away. From the mouth of the Hudson River in New York and from glacial deposits on Long Island and southern New England. Midway along this coast, at Sandy Hook, New Jersey, an average of 2,000 tons of sandy sediment a day will move past any point on the beach. As a result of these longshore currents, some beaches have been called rivers of sand. Tidal currents when tides rise and fall along an open coastline. Water moves in and out from the shore as a broad sheet. If the flow is channeled by a bay with a narrow entrance or by islands, the moving water funnels into a tidal current, which is a flow of ocean water caused by tides. Tidal currents can be intense where large differences exist between high and low tides and narrow constrictions occur in the shoreline. On parts of the west coast of British Columbia, a diesel-powered fishing boat cannot make headway against tidal currents flowing between closely spaced islands. Fishermen must wait until the tide, and hence the tidal current, reverses direction before proceeding. Emergent and submergent coastlines. Geologists have found drowned river valleys and fossils of land animals on continental shelves beneath the sea. They have also found sedimentary rocks containing fossils of fish and other marine organisms in continental interiors. As a result, we infer that sea level has changed, sometimes dramatically, throughout geologic time. An emergent coastline forms when a portion of a continent that was previously underwater becomes exposed as dry land. Falling sea level or rising land can cause emergence. As explained in section on beaches, many emergent coastlines are sandy. In such cases, the delivery of sandy sediment to the coastline is high enough to cause the shoreline to migrate seaward. In contrast, a submergent coastline develops when the sea floods low-lying land and the shoreline moves inland. Submergence occurs when sea level rises or coastal land sinks. A submergent coast is commonly irregular, with many bays, sea cliffs, and headlands. The coast of Maine, with its numerous fjords, inlets, and rocky bluffs, is a classic submergent coastline. Small, sandy beaches form in some protected coves, but most of the shoreline is rocky and steep because it consists of eroding bedrock and glacial sediment. Factors that cause coastal emergence and submergence. Tectonic processes can cause a coastline to rise or sink. Isostatic adjustment can also depress or elevate a portion of a coastline. About 18,000 years ago, a huge continental glacier covered most of Scandinavia, causing it to sink isostatically. As the lithosphere settled, the displaced asthenosphere flowed southward, causing the Netherlands to rise. When the ice melted, the process reversed as the asthenosphere flowed back from below the Netherlands to Scandinavia. Today, Scandinavia is rebounding and the Netherlands is sinking. During the Pleistocene glaciation, Canada was depressed by the ice, and asthenosphere rock flowed southward. Today, the asthenosphere is flowing back north, much of Canada is rebounding, and much of the continental United States is sinking. Sea level can also change globally. A global sea level change, called eustatic sea level change, occurs by three mechanisms: the growth or melting of glaciers, changes in water temperature, and changes in the volume of the midoceanic ridge. During an ice age, vast amounts of water are withdrawn from the sea to form continental glaciers, causing sea level to drop and coastlines around the world to emerge. Similarly, when glaciers melt, sea level rises globally, causing global submergence of coastlines. Seawater expands when it is heated and contracts when it is cooled. Although this change is not noticeable in a glass of water, the volume of the oceans is so great that a small temperature change can alter sea level measurably. As a result, global warming causes sea level rise, and global cooling leads to falling sea level. Temperature changes and glaciation are linked. When global temperature rises, seawater expands and glaciers melt. Thus, even minor global warming can lead to a large sea level rise. The opposite effect is also true: when temperature falls, seawater contracts, glaciers grow, and sea level falls. As explained in Chapter 15, changes in the volume of the midoceanic ridge can also affect sea level. The ridge displaces seawater. When lithospheric plates spread slowly from the midoceanic ridge, they create a narrow ridge that displaces relatively little seawater, resulting in low sea level. In contrast, rapidly spreading plates produce a high-volume ridge that displaces more water, causing a global sea level rise. At times in Earth's history, spreading has been relatively rapid, and as a result, global sea level has been high. Beaches. When most people think about going to the beach, they think of gently sloping expanses of sand. However, a beach is any strip of shoreline that is washed by waves and tides. Although many beaches are sandy, others are swampy or rocky. A beach is divided into three zones, although only two of these are exposed. Above the sea surface, the shore face extends from mean low tide to mean fair weather wave base. The shore face typically slopes seaward and is the zone of wave shoaling, in which waves slow down, steepen, and break, expending mechanical energy against the bottom. The foreshore, also called the intertidal zone, lies between mean high and low tides and is alternately exposed to the air at low tide and covered by water at high tide. The backshore exists above the foreshore and is usually dry but is washed over by waves during storms. It commonly slopes gently landward as a result of sediment delivered and deposited by storm waves losing energy as they wash inland. Many terrestrial plants cannot survive in salt water, so specialized, salt-resistant plants live in the backshore. The backshore can be wide or narrow, depending on its topography, the local tidal difference, and the frequency and intensity of storms. In a region where the land rises steeply, the backshore may be a narrow strip. In contrast, if the coast consists of low-lying plains and if coastal storms occur regularly, the backshore may extend several kilometers inland. If weathering and erosion occur along all coastlines, why are some beaches sandy and others rocky? The answer lies partly in the fact that most sand is not formed by weathering and erosion at the beach itself. Instead, several processes transport sand to a seacoast. Rivers carry large quantities of sand, silt, and clay to the sea and deposit it on deltas that may cover thousands of square kilometers. In some coastal regions, glaciers deposited large quantities of sandy till along coastlines during the Pleistocene Ice Age. In tropical and subtropical latitudes, eroding reefs supply carbonate sand to nearby beaches. A sandy coastline is one with abundant sediment. From one or more of these sources, longshore currents transport and deposit the sand along the coast. Much of the sand carried by these currents accumulates on underwater offshore bars. Thus, a great deal of sand may be stored offshore from a beach. If such a coastline emerges, this vast supply of sand becomes exposed as dry land and is available, if eroded, for building more beaches and more offshore bars. Thus, sandy beaches are abundant on emergent coastlines. In contrast, rocky coastlines occur where sediment from any of these sources is scarce. With no abundant sources of sand, small sandy beaches may form in protected bays, but most of the coast will be rocky. On a submergent coastline, rising sea level puts the stored offshore sand even farther out to sea and below the depth of waves. As a result, submergent coastlines commonly have beaches that are rocky, not sandy. Sandy coastlines. A spit is a small, finger-like ridge of sand or gravel that extends outward from a beach. As sediment migrates along a coast, the spit may continue to grow. A well-developed spit may rise several meters above high tide level and may be tens of kilometers long. A spit may block the entrance to a bay, forming a behemoth bar. A spit may also extend outward into the sea, creating a trap for other moving sediment. A barrier island is a long, low-lying sandy island that extends parallel to the shoreline. It looks like a beach or spit and is separated from the mainland by a sheltered body of water called a lagoon. Barrier islands extend along the east coast of the United States from New York to Florida. They are so nearly continuous that a sailor in a small boat can navigate the entire coast inside the barrier island system and remain protected from the open ocean. Most of the time. Barrier islands also line the Texas Gulf Coast. Barrier islands form in several ways. The two essential ingredients are a large supply of sand and the waves or currents to transport it. If a coast is shallow for several kilometers outward from shore, breaking storm waves may carry sand toward shore and deposit it just offshore as a barrier island. Alternatively, if a longshore current veers out to sea, it slows down and deposits sand where it reaches deeper water. Waves may then pile up the sand, forming a barrier island. Other mechanisms that create barrier islands involve sea level change. Underwater sandbars may be exposed as a coastline emerges. Alternatively, sand dunes or beaches may form barrier islands if a coastline sinks. Development on sandy coastlines. The Atlantic coast of the United States is fringed with the longest chain of barrier islands in the world. Many seaside resorts are built on these islands, and developers often ignore the fact that they are transient and changing landforms. If the rate of erosion exceeds that of deposition for a few years in a row, a barrier island can shrink or disappear completely, leading to destruction of beach homes and resorts. In addition, barrier islands are especially vulnerable to hurricanes, which can wash over low-lying islands and move enormous amounts of sediment in a very brief time. In September 1996, Hurricane Fran flattened much of Topsail Island, a low-lying barrier island in North Carolina. Geologists were not surprised, because the homes were not only built on sand but they were built on sand that was virtually guaranteed to move. As a second example, Long Island extends eastward from New York City and is separated from Connecticut by Long Island Sound. Longshore currents flow westward, eroding sand from glacial deposits at the eastern end of the island and depositing it to form beaches and barrier islands on the south side of the island. At any point along the beach, the currents erode and deposit sand at approximately the same rates. Geologists calculate that the supply of sand at the eastern end of the island is large enough to last a few hundred years. When the glacial deposits at the eastern end of the island become exhausted, however, the flow of sand will cease. Then the entire coastline will erode and the barrier islands and beaches will disappear. Now let's narrow our time perspective and look at a Long Island beach over a season or during a single storm. Over this time frame, the rates of erosion and deposition are not equal. Thus, beaches shrink and expand with the seasons or the passage of violent gales. In the winter, violent waves and currents erode beaches, whereas sand accumulates on the beaches during the calmer summer months. In an effort to prevent these seasonal fluctuations and to protect their personal beaches, Long Island property owners have built stone barriers called groins from shore out into the water. The groin intercepts the steady flow of sand moving from the east and keeps that particular part of the beach from eroding. But the groin impedes the overall flow of sand. West of the groin, the beach erodes as usual, but the sand is not replenished because the upstream groin traps it. As a result, beaches downcurrent from the groin erode away. The landowners living downcurrent from groins may then decide to build other groins to protect their beaches. The situation has a domino effect, with the net result that millions of dollars are spent in ultimately futile attempts to stabilize a system that was naturally stable in its own dynamic manner. Storms pose another dilemma. Hurricanes commonly strike Long Island in the late summer and fall, generating storm waves that flatten dunes, erode beaches, and transport large volumes of sand into nearby salt marshes, disrupting the ecosystem there. When the storms are over, gentler waves and longshore currents carry sediment back to the beaches and rebuild them. As the sand accumulates again, salt marshes rejuvenate and the dune grasses grow back within a few months. Unfortunately, these short-term fluctuations are incompatible with human ambitions. People build houses, resorts, and hotels on or near the shifting sands. The owner of a home or resort hotel cannot allow the buildings to be flooded or washed away. Therefore, property owners construct large seawalls along the beach. When a storm wave rolls across an undeveloped low-lying beach, it dissipates its energy gradually as it flows over the dunes and transports sand. The beach is like a judo master who defeats an opponent by yielding to the attack, not countering it head-on. A seawall interrupts this gradual absorption of wave energy. The waves crash violently against the barrier and erode sediment at its base until the wall collapses. It may seem surprising that a reinforced concrete seawall is more likely to be permanently destroyed than a beach of grasses and sand dunes, yet this is often the case. Rocky coastlines. A rocky coastline is one without any of the abundant sediment sources described previously. In many areas on land, bedrock is exposed or covered by only a thin layer of soil. If this type of sediment-poor terrain is submerged, and if there are no other sources of sand, the coastline is rocky. A wave-cut cliff forms when waves erode the headland into a steep profile. As the cliff erodes, it leaves a flat or gently sloping wave-cut platform. If waves cut a cave into a narrow headland, the cave may eventually erode all the way through the headland, forming a scenic sea arch. When an arch collapses or when the inshore part of a headland erodes faster than the tip, it leaves behind a pillar of rock called a sea stack. As waves continue to batter the rock, eventually the sea stack crumbles. If the sea floods a long, narrow, steep-sided coastal valley, a sinuous bay called a fjord is formed. Fjords are common at high latitudes, where rising sea level has flooded coastal U-shaped valleys scoured by Pleistocene glaciers. Fjords may be hundreds of meters deep, and often the cliffs at the shoreline drop straight into the sea. Life in the sea. On land, most photosynthesis is conducted by multicellular plants, including mosses, ferns, grasses, shrubs, and trees. Large animals such as cows, deer, elephants, and bison consume the plants. In contrast, most of the photosynthesis and consumption in the ocean is carried out by small organisms called plankton. Many plankton are single-celled and microscopic, others are more complex and are up to a few centimeters long. One major difference between terrestrial and aquatic ecosystems is that on land soil nutrients are abundant on the surface, where light is also abundant. However, in the oceans, light is available only in the photic zone, which ranges from the surface downward up to 200 meters in the open ocean but typically is shallower closer to shore where the water is more turbid. In contrast to light, nutrients in the oceans tend to settle to the dark depths. Plankton live mostly within a few meters of the sea surface, where light is available. However, the growth and productivity of these organisms is limited by the fact that most of the nutrients, such as nitrogen, iron, and phosphorus, are incorporated into the tissue of planktonic organisms that die and sink to the bottom, carrying the nutrients with them. If the surface waters are not replenished by a fresh supply of nutrients, their productivity will be limited. Phytoplankton conduct photosynthesis like land-based plants do. Therefore, they are the base of the food chain for aquatic animals. Although phytoplankton are not readily visible, they are so abundant that they supply about 50% of the oxygen in our atmosphere. Zooplankton are tiny animals that feed on the phytoplankton. The larger and more familiar marine plants and animals play a relatively small role in overall oceanic photosynthesis and consumption. However, many of these organisms are important to humans as a major source of protein. World fisheries. The shallow water of a continental shelf supports large populations of marine organisms. In addition, many deep-sea fish spawn in shallow water within 1 or 2 kilometers of the shoreline. Shallow zones in bays, lagoons, and estuaries are especially hospitable to life because they have easy access to the deep sea, lower salinity than the open ocean, a high concentration of nutrients originating from land and sea, shelter, and abundant plant life rooted to the seafloor in addition to the phytoplankton floating on the surface. As a result, about 99% of the marine fish caught every year are harvested from the shallow waters of the world's continental shelves. Historically, fishing pressure by humans has impacted fish populations, causing a shift in the type of fish targeted, which typically has moved down the food chain. For example, in 1970, fishermen harvested 3 million tons of cod, a predatory fish. This large catch turned out to be biologically unsustainable and had declined to 1 million tons by 1993. In 1995, biologists suspended cod fishing in many areas to allow the populations to recover. In 1978, stocks of herring and mackerel, both of which eat mostly plankton and therefore are lower on the food chain, began to decline, so boats switched nets to trawl for squid. In the 1980s, however, the squid population began to decline. Thus, fishing pressure has worked through the food chain, disrupting the entire ecosystem. In one study, oceanographers documented research showing that industrial fishing fleets have caused a 90% reduction of large predatory fish such as tuna, marlin, swordfish, cod, halibut, and flounder. At the advent of intensive commercial fishing 100 years ago, most fleets caught 6 to 12 fish for every 100 baited hooks. Today, despite sophisticated electronic and aerial fish-finding techniques, the catch rate has pointed out that as industrial fishing depletes large, long-lived predatory species that occupy the highest levels of the food chain, move down to the next level, to species that tend to be smaller, shorter-lived, and less valuable. As a result, fishers worldwide now fill their nets with plankton-eating species such as squid, jacks, mackerel, sardines, and invertebrates including oysters, mussels, and shrimp. Commercial fishermen now work harder, spend more time, and consume more fuel to capture smaller quantities of less valuable species. They are essentially fishing down the marine food web. The authors of the study continue, but the cycle of fishing down the marine food web can't go on forever. At the current rate of descent, it will take only 30 to 40 years to fish down to the level of plankton. The UN's Food and Agricultural Organization predicted that world fish harvests would remain fairly constant at around 90 million tons per year until the year 2010, but thereafter, ecosystem destruction and overfishing would lead to sharp declines in fish populations and harvests. One 2018 study analyzed the FOA data and compared it to a reconstructed data set from its own analysis of 10 years locally collected fishing data from around the world. The 2018 study indicates that, because the FOA relies on official government numbers for fish caught, it is missing the large size of the fish catches for subsistence, artisanal, or recreational purposes. Many countries are neither interested in nor have the capacity to tally catches from these fisheries, and some nations have altered the reported catch numbers for political reasons. According to the 2018 study, the global catch related to subsistence, artisanal, and recreational fisheries represented 25% of the total catch over the past decade. Although the FOA has defended its data-gathering methodology for global fish stocks, many wild stocks continue to decline without globally agreed catch limits designed to replenish fish stocks. Collective international adherence to a set of global catch limits, as well as a broader data-gathering system for determining what fish species are harvested, along with the location and date of the catch, is needed. A reef is a wave-resistant ridge or mound built by corals, oysters, algae, or other marine organisms. Because corals need sunlight and warm, clear water to thrive, coral reefs develop in shallow tropical seas where little suspended clay or silt muddies the water. As the corals die, their offspring grow on their remains. Oyster reefs, on the other hand, form in temperate estuaries and can grow in more turbid water. Globally, coral reefs cover about 600,000 square kilometers, about the area of France, but they spread out in long, thin lines. They are extraordinarily productive ecosystems because the corals provide shelter for many invertebrates, fish, and other marine organisms. Within the past 50 years, 10% of the world's coral reefs have been destroyed and an additional 30% are in critical condition. Several factors have contributed to this destruction. Increased levels of carbon dioxide in Earth's atmosphere have caused higher concentrations of the gas to be dissolved in the world's oceans, causing ocean acidification and making it more difficult for calcium carbonate secreting organisms, such as corals, to live. Corals thrive best in a narrow temperature range. In recent years, oceanographers have compiled considerable evidence that sea surface temperatures have become warmer in recent decades, and the warm water is leading to massive death of corals. Silt from cities, urban roadways, farms, and improper logging smother the delicate reef organisms. Fertilizer runoff from farms and sewage runoff from cities have added nutrients to coastal waters, feeding coral predators and lowering the levels of dissolved oxygen levels below the level required for oxygen-respiring organisms, including corals, to survive. For example, a 2017 study by National Geographic reported that nutrient-rich runoff from the Mississippi River caused the development of New Jersey-sized dead zone along the Louisiana and much of the Texas coasts. The dead zone is characterized by levels of dissolved oxygen too low to sustain life and is formed because high concentrations of nutrients, especially nitrogen and phosphorus, are delivered by the Mississippi River. The Mississippi River drainage is by far the largest in North America and includes nearly the entirety of the American breadbasket, from Montana to Pennsylvania. Runoff in the Mississippi drainage picks up fertilizers, soil particles, animal wastes, and sewage. These sources combine to produce huge algal blooms in the northern Gulf of Mexico, altering the food chain and depleting dissolved oxygen in the water. The size and dimensions of the dead zone fluctuate along with seasonal discharge from the Mississippi River, large rainfall events, and hurricanes. Global warming and rising sea level. Sea level has risen and fallen repeatedly in the geologic past, and coastlines have emerged and submerged throughout Earth's history. During the past 40,000 years, sea level has fluctuated by about 150 meters, primarily in response to the growth and melting of glaciers. The rapid sea level rise that started about 18,000 years ago began to level off about 7,000 years ago. By coincidence, humans began to build cities about 7,000 years ago. Thus, civilization developed during a short time when sea level was relatively constant. Shore-based gauging stations and satellite radar studies agree that global sea level is presently rising at about 3 millimeters per year. Thus, if present rates continue, sea level will rise about 20 centimeters in 100 years. Such a rise would be significant along very low-lying areas such as the Netherlands, Bangladesh, and many Pacific islands. Consequences of rising sea level vary with location and economics. The wealthy, developed nations could build massive barriers to protect cities and harbors from a small sea level rise. In regions where global sea level rise is compounded by local tectonic sinking, dikes are already in place or planned. Portions of Holland lie below sea level, and the land is protected by a massive system of dikes. In London, where the high tide level has risen by 1 meter in the past century, multi-million-dollar storm gates have been built on the Thames River. Venice, Italy, which is built over canals at sea level, has flooded frequently in recent years, and here too expensive engineering projects are underway. Rising sea level has resulted in erosion along much of the coastline along the Gulf Coast and eastern seaboard, reducing the size of nearshore wetlands which are needed to help decompose wastes and protect low-lying coastal areas from the effects of hurricanes. However impressive the engineering of modern urban coastlines becomes, it is unlikely that coastal cities will ever be fully protected against a dramatic sea level rise of several meters. Coastal cities worldwide would be inundated. Moreover, many poor countries cannot afford coastal protection even for a modest sea level rise. For example, a 1-meter rise in sea level would flood roughly 17% of the land area of Bangladesh, displacing tens of millions of inhabitants. Chapter 17, The Atmosphere. Introduction. Nearly every multicellular organism needs oxygen to survive. If the oxygen abundance in the atmosphere were to drop below 44% of its current value, life on Earth as we know it would perish. If oxygen is essential to most life, would we be better off if we had an even greater supply? The answer is yes, to a limit. Even at sea level, athletes can enhance their performance by breathing a small amount of bottled oxygen. But, paradoxically, too much oxygen is poisonous. If you breathe air that has 55% or more oxygen than is found at sea level, your body metabolism becomes so rapid that essential molecules and enzymes decompose. In addition, fires burn more rapidly with increased oxygen concentration. If the oxygen level in the atmosphere were to rise significantly, extremely large wildfires would engulf the planet, altering ecosystems as we know them. Earth is the near-perfect size and distance from a stable and medium-temperature star to permit optimal atmospheric conditions for life. But Earth's atmospheric composition and temperature are not determined solely by planetary size and distance from the Sun. Rather, our planet's environment is finely regulated by interactions among Earth systems. Over the past 4 billion years, the Sun's output has slowly increased. However, Earth's atmospheric temperature has remained remarkably constant because of interactions among Earth systems. In this chapter, we will explore these interactions and see how they led to the structure and dynamics of Earth's atmosphere today. Earth's early atmospheres. Scientists have revealed a nearly continuous record of rocks of different ages, from 4.04 billion years ago to the present. Therefore, when they study the history of Earth's continental crust, they can analyze the chemical composition of these ancient rocks for clues. Unfortunately, there are no samples of very old atmospheres. So how can we determine atmospheric composition millions to billions of years ago? Many gaps in understanding exist, but the history described next comes from information derived from computer modeling as well as the direct study of rocks. Modeling involves calculations about how atmospheric gases would have behaved under the presumed environment of early Earth. To test these models, scientists study the geochemistry of ancient rocks. Rocks react with water and air, and the nature of these reactions depends on the geochemistry of the entire system. By studying the rocks that existed in a specific time period, scientists deduce the other components of the system that would have produced those reactions. For example, as we will discuss, iron reacts with oxygen to produce iron oxides. Thus, if we find iron oxides in certain types of sedimentary rocks that formed 2.6 billion years ago, we deduce that oxygen must have been present in the air and water at that time. The first atmospheres, 4.6 to 4.0 billion years ago, our solar system formed from a cold, diffuse cloud of interstellar gas and dust. About 99.8% of this cloud was composed of the two lightest elements, hydrogen and helium. Consequently, when Earth formed, its primordial atmosphere was composed almost entirely of these two light elements. But because Earth is relatively close to the Sun and its gravitational force is relatively weak, its primordial hydrogen and helium atmosphere rapidly boiled off into space and escaped. Table 17. 1 shows this and the subsequent atmospheres of Earth described in this chapter. In Chapter 15, we learned that most of the volatile compounds that form Earth's hydrosphere, atmosphere, and biosphere originated from outer parts of the solar system. Recall that, in its infancy, the solar system was crowded with bits of rock, comets, ice chunks, and other debris left over from the initial coalescence of the planets. These bolides crashed into the planet in a near-continuous rain that lasted almost 800 million years. Carbonate compounds and carbon-rich rocks reacted under the heat and pressure of impact to form carbon dioxide. Ice quickly melted into water. Ammonia, common in the icy tail of comets, reacted to form nitrogen when life began, 4.0 to 2.6 billion years ago. The carbon dioxide, water, and nitrogen atmosphere changed as volatiles escaped from Earth's mantle to the surface in volcanic eruptions, in a process called outgassing. In 1953, Stanley Miller and Harold Urey hypothesized, on the basis of little direct modeling, that by 4 billion years ago, Earth's atmosphere consisted primarily of methane, ammonia, hydrogen, and water. They mixed these gases in a glass flask and fired sparks across the flask to simulate Earth's early atmosphere, beset by lightning storms. Amino acids, the building blocks of proteins, formed in the flask. The Miller-Urey model immediately became popular because scientists speculated that the first living organisms formed by accretion of these abiotic amino acids. In the early 1970s, the idea of a methane-ammonia-hydrogen atmosphere was largely discredited, and most scientists postulated that the Hadean atmosphere was composed mainly of carbon dioxide, with smaller amounts of nitrogen, water, and other gases. However, in 2002, geologists analyzed the isotopic geochemistry of single grains of zircon that are the oldest known preserved mineral grains on Earth, dating between 4.5 and 4.0 billion years before present. Zircon is a silicate mineral that only forms in rocks with a silica-rich, felsic composition. It does not exist in the silica-poor mafic and ultramafic rocks, so the geologists concluded that granitic crust had formed within the first 500 million years of Earth's history. In addition, the isotopic composition of oxygen making up the silicate anionic groups within the zircon mineral crystal was high enough for the geologists to conclude that the surface of the early Earth was cold, not hot, and that water would have been mostly liquid. Subsequently, in 2005, scientists used models of Earth's Hadean geosphere to calculate how gases trapped in the interior would react with rocks and minerals in the planet's interior and surface. These results also suggested that early Earth had a cool surface that included liquid water. From this work, one unobvious, yet pivotal, question emerged: when did Earth's core form? Earth's core is the deepest layer of the geosphere. The atmosphere is a thin veneer surrounding the crust. How could one affect the other? Recall that the core is composed primarily of iron and nickel. Before Earth's interior segregated into a layered core and mantle, the mantle contained more iron than it does today. Then, when iron settled into the core, the mantle became relatively iron-poor. Modern hypotheses state that Earth was hot at the time of its formation and that most of the planet's iron was sequestered in its core shortly after the planet evolved, leaving an iron-poor mantle behind. Because mantle rocks rise to the surface through volcanic eruptions, the composition of the mantle directly influences the composition of erupted material, including the types of volatiles that are emitted. By modeling the reactions of volatiles in an iron-poor mantle, researchers concluded in 2005 that the delivery of these volatiles to the atmosphere resulted in a composition that included not only large amounts of hydrogen, as Miller and Urey postulated, but also high concentrations of carbon dioxide, as later models had proposed. Even more recently, a different set of scientists argued that the Earth's early surface temperatures were significantly warmer than today, with estimates of surface temperatures between 45 degrees Celsius and 85 degrees Celsius. Models of Earth and its evolution are constantly changing. Scientists propose hypotheses and theories, consider new ideas, and often other scientists disagree. This is the nature and the joy of science. In a review article, Christopher Chiba of SETI Institute and Stanford University wrote that current disagreement about the composition of Earth's earliest atmospheres makes it a great time for young scientists to enter the field, but it also reminds us that some humility regarding our favorite models is in order. Further constraining the composition and evolution of Earth's earliest atmosphere continues to be a major scientific challenge that will involve much additional research, discussion, and, quite likely, disagreement among different scientists. Life, iron, and the evolution of the modern atmosphere as explained. Previously, the first living organisms may have formed by the accretion of complex abiotic organic molecules formed in early Earth's surficial environments. However, complex organic molecules, such as those postulated to have led to the first organisms, become oxidized and destroyed in an oxygen-rich environment. These chemical reactions suggest that if large amounts of oxygen were present in Earth's early atmosphere, the abiotic precursors to living organisms could not have formed. A geochemist can determine whether a rock formed in an oxygen-rich or an oxygen-poor environment by analyzing the mineral assemblage and geochemistry of the rock and applying what is currently known about the thermal and chemical conditions needed to form that suite of minerals. Recent studies of Earth's oldest rocks indicate that the atmospheric oxygen concentration in early Precambrian time was extremely low. These results suggest that the molecules necessary for the emergence of living organisms, namely methane, ammonia, hydrogen, and water, would have been preserved in the primordial atmosphere. Although life could not have emerged in an oxygen-rich environment, complex multicellular life requires an oxygen-rich atmosphere to survive. How, then, did oxygen become abundant in our atmosphere? The world's earliest organisms probably were chemoautotrophs that obtained their energy from reactions with minerals such as iron and sulfur in an extremely inefficient process. Recall from Chapter 15 that chemoautotrophic bacteria are common today around vents of extremely hot, hydrothermal water emanating from parts of the mid-oceanic ridge. Later, organisms subsisted, in part, by eating each other. But these food chains were limited because there were only a few organisms on Earth. A crucial step in evolution occurred when primitive bacteria evolved the ability to harness the energy in sunlight and produce organic tissue. This process, known as photosynthesis, is the foundation for virtually all modern life. During photosynthesis, organisms convert carbon dioxide and water to organic sugars. They release oxygen as a byproduct. In 1972, an English chemist named James Lovelock hypothesized that the oxygen produced by primitive organisms gradually accumulated, creating the modern atmosphere. By late Precambrian time, atmospheric oxygen concentration had reached the critical level needed to sustain efficient metabolism. As a result, multicellular organisms evolved and the biosphere as we know it was born. Lovelock was so overwhelmed by the intimate connection between living and non-living components of Earth's systems that he likened our planet to a living creature, which he called Gaia. The Lovelock hypothesis, now over 45 years old, remains generally accepted, but scientists are still investigating many of the details. For example, blue-green algae called cyanobacteria began producing oxygen 2.7 billion years ago, but appreciable quantities of oxygen didn't begin to appear in the atmosphere until 2.4 billion years ago, in the first great oxidation event, when the concentration of atmospheric oxygen rose abruptly. The production of oxygen by cyanobacteria beginning 2.7 billion years ago started slowly, and for about 700 million years thereafter, atmospheric oxygen concentration remained far below today's level. At times during this 700 million year period, Earth's atmosphere may have been anoxic, meaning there was no oxygen. These abrupt variations in the concentration of oxygen in Earth's earliest atmosphere, from periods of anoxia on the one hand to the first great oxidation event 2.4 billion years ago on the other, strongly suggest that the presence of oxygen was driven by a mechanism involving a chemical threshold. To understand the mechanism behind this threshold reaction, we must study atmosphere, geosphere and atmosphere, biosphere systems interactions. Systems interactions that affected oxygen concentration in Earth's early atmosphere. Geosphere, atmosphere interactions. Even though large quantities of iron coalesced into Earth's core, appreciable quantities remained in the mantle and crust. Today's crust, for example, is about 5% iron by weight. The iron that remained near the surface during early Earth played an important role in concentrating oxygen in Earth's early atmosphere. Oxygen gas dissolves in water. As a result, when early cyanobacteria released oxygen, some of the gas dissolved in seawater. In an oxygen-poor environment, iron also dissolves in water. However, when oxygen is abundant, the dissolved oxygen reacts with dissolved iron and causes the iron to precipitate rapidly as iron oxide minerals. Because iron is soluble in water lacking dissolved oxygen, large amounts of iron dissolved in the early Precambrian ocean at times when its concentration of dissolved oxygen was below the threshold level. However, when the concentration of dissolved oxygen from cyanobacteria rose beyond the threshold, iron that had been dissolved in the seawater precipitated rapidly as iron oxide minerals. These minerals settled to the seafloor, forming a layer there. This process also removed oxygen from the water, explaining why the oxygen concentration in the atmosphere didn't rise at this time in Earth's early history, even though cyanobacteria were releasing oxygen as a gas. Roughly 90% of the iron ore that is mined globally comes from banded iron formation, chemical sedimentary rock that consists of alternating layers of iron oxide and chert a few centimeters thick. Most of the banded iron formation on Earth is between 2.6 and 1.9 billion years old and is inferred to have originated when the oxygen level in the seas hovered near the threshold at which soluble iron combined with oxygen to form iron oxide minerals. At times when dissolved oxygen concentrations were high enough, the oxygen would combine with dissolved iron to precipitate iron oxide minerals, which formed a layer on the seafloor. The formation of these minerals extracted oxygen as well as iron from the seawater, lowering its oxygen concentration below the threshold. Then dissolved iron accumulated again in the seas from chemical weathering of exposed rock, while the oxygen was slowly replenished by photosynthesizing cyanobacteria. During that time, clay and other minerals washed from the continents and accumulated on the seafloor as they do today, forming the thin layers of silicate minerals that lie between the iron-rich layers in banded iron formation. When the oxygen concentration rose above the threshold again, another layer of iron oxide minerals formed. Banded iron formations contain thousands of alternating layers of iron minerals and silicates and can cover tens of square kilometers the great volume of the iron formations, coupled with the fact that they continue to form from 2.6 to 1.9 billion years ago, suggests that the reactions that formed them must have kept the levels of dissolved oxygen close to the threshold for about 700 million years. Thus the iron-rich rocks that support our industrial society were formed by interactions among early photosynthesizing organisms, sunlight, air, and the oceans. Biosphere, atmosphere interactions in the primordial atmosphere. Free oxygen also reacted with hydrogen to form water. This process helped keep the oxygen concentration in the atmosphere low. However, after life evolved, bacteria in the oceans removed atmospheric hydrogen in a process that produced methane. When the hydrogen concentration decreased sufficiently, the concentration of free oxygen in the atmosphere could rise again. Whatever the exact combination of biological and geochemical processes, evidence in the rocks indicates that the oxygen concentration in the atmosphere remained low and then jumped suddenly from trace to appreciable quantities approximately 2.4 billion years ago. Evolution of the modern atmosphere. Several deposits of banded iron formed after the first great oxidation event, and this process continued to remove oxygen that was released during photosynthesis. The last, major banded iron layer was deposited about 1.9 billion years ago, but the oxygen concentration in the atmosphere did not increase dramatically. At least two more critical steps were required before efficient multicellular organisms could evolve. The sun emits energy largely in the form of high-energy ultraviolet light. These rays are energetic enough to break apart complex molecules and kill evolving multicellular organisms. But high-altitude oxygen absorbs ultraviolet radiation in a process that forms ozone. Thus, the oxygen concentration couldn't increase in the lower atmosphere until appreciable concentrations first accumulated in the upper atmosphere. To summarize, oxygen, largely produced by the earliest photosynthetic organisms, was not only necessary for life as we know it today, but as ozone it also protected multicellular life by filtering out harmful solar rays. Multicellular plants and animals emerged in late Precambrian time, between 1 billion and 543 million years ago. About 600 million years ago, the oxygen level in the atmosphere increased rapidly a second time, in a process called the Second Great Oxidation Event. What changed abruptly? 3 billion years after the last banded iron layers were deposited to allow oxygen to accumulate. Scientists propose that prior to 600 million years ago, biological decay was almost as rapid as photosynthesis. Therefore, the oxygen that was released into the atmosphere was immediately consumed during respiration, according to the following reactions. During photosynthesis, carbon dioxide 1 water sugars 1 oxygen. During respiration and decay, sugars 1 oxygen carbon dioxide 1 water. Then, beginning abruptly 600 million years ago, several processes occurred that allowed preservation of organic matter in sediments before it could decay. These processes effectively removed the organic carbon from the system, thereby causing the opposing reactions above to lean in the direction favoring photosynthesis. Stated differently, environmental conditions that allowed the generation but subsequent removal and storage of organic carbon in sediment also were conducive to the expansion of photosynthetic organisms and the generation of much oxygen as a byproduct. All the proposed processes for sequestering organic matter involve complex reactions among Earth's 4 spheres. Geochemical processes produced an abundance of clays 600 million years ago. These clays buried and preserved organic matter on the seafloor. Zooplankton evolved in the seas. These organisms produced dense, organic latent feces that sank rapidly to the seafloor, where they accumulated in the clays and were subsequently buried, thereby removing organic carbon from the system. Simple lichens evolved on land. The lichens accelerated weathering, and the weathered ions washed into the sea and provided nutrients for phytoplankton. In turn, the phytoplankton fed the zooplankton, which sequestered nutrients as described previously. Thus, numerous complex chemical, physical, and biological processes combined to set the stage for the Second Great Oxidation Event. Earth's atmosphere not only sustains us but it insulates Earth's surface as winds distribute the sun's heat around the globe so that the surface is neither too hot nor too cold for life to exist. Clouds form from water vapor in the atmosphere and rain falls from clouds. In addition, the atmosphere filters out much of the sun's ultraviolet radiation, which can destroy living tissue and cause cancer. The atmosphere carries sound. Without air we would live in silence. Without an atmosphere, airplanes and birds could not fly, wind would not transport pollen and seeds, the sky would be black rather than blue, and no reds, purples, and pinks would color the sunset. When we understand this complex web of interacting processes and realize that we are the only planet in the solar system to be so fortunate, we can only marvel at the fragility of Earth's atmosphere. The modern atmosphere is mostly gas, but also contains droplets of liquid water and suspended particles of dust. The gaseous composition of dry air is roughly 78% nitrogen, 21% oxygen, and 1% other gases. Nitrogen, the most abundant gas, does not react readily with other substances. Oxygen, though, reacts chemically as fires burn, iron rusts, and plants and animals respire. Carbon dioxide, which by some models formed as much as 80% of Earth's early atmosphere, is a trace gas in the modern atmosphere, with a concentration of only 0.035%. The types and quantities of gases, water vapor, droplets, and dust vary with both location and altitude. In a hot, steamy jungle, air may contain 5% water vapor by weight, whereas in a desert or cold polar region only a small fraction of a percent may be present. If you sit in a house on a sunny day, you may see a sunbeam passing through a window. The visible beam is light reflected from tiny specks of suspended dust. Clay, salt, pollen, bacteria, viruses, bits of cloth, hair, and skin are all components of dust. People travel to the seaside to enjoy the salt air. Visitors to the Great Smoky Mountains in Tennessee view the bluish, hazy air formed by sunlight reflecting from pollen and other dust particles. Within the past century, humans have altered the chemical composition of the atmosphere in many different ways. We have increased the carbon dioxide concentration by burning fossil fuels and igniting wildfires. Factories release chemicals into the air, some benign, others poisonous. Smoke and soot change the clarity of the atmosphere. These changes are discussed in the section on air pollution. Atmospheric pressure. The molecules in a gas zoom about in a random manner. For example, at 20 degrees Celsius an average oxygen molecule is traveling at 425 meters per second. In the absence of gravity, or where there are temperature differences or other perturbations, a gas will fill a space homogeneously. Thus, if you float a cylinder of gas in space, the gas would disperse until there is an equal density of molecules and equal pressure throughout the cylinder. In contrast, gases that surround Earth are perturbed by many influences, which ultimately create the complex and turbulent atmosphere that helps shape the world we live in. Within our atmosphere, gas molecules zoom around, as in the imaginary cylinder, but in addition, gravity pulls them downward. As a result of this downward force, more molecules concentrate near the surface of Earth than at higher elevations. Therefore, the atmosphere is denser at sea level than it is at higher elevations, and the pressure is higher. Density and pressure then decrease exponentially with elevation. At an elevation of about 5,000 meters, the atmosphere contains about half as much oxygen as it does at sea level. If you ascended in a balloon to 16,000 meters above sea level, you would be above 90% of the atmosphere and would need an oxygen mask to survive. At an elevation of 100 kilometers, pressure is only 0.00003 that of sea level, approaching the vacuum of outer space. There is no absolute upper boundary to the atmosphere. Atmospheric pressure, often called barometric pressure, is measured with a barometer. A simple but accurate barometer is constructed from a glass tube that is sealed at one end. The tube is evacuated and the unsealed end placed in a dish of a liquid such as mercury. The mercury rises in the tube because atmospheric pressure depresses the level of mercury in the dish, but there is no air in the tube to counter that pressure, so the surface of the mercury rises. At sea level, mercury rises approximately 76 centimeters, or 760 millimeters, into an evacuated tube. Meteorologists express pressure in inches or millimeters of mercury, referring to the height of the column of mercury in a barometer. They also express pressure in bars and millibars. A bar is approximately equal to sea level atmospheric pressure. A millibar is 0.001 of a bar. A mercury barometer is a cumbersome device nearly a meter tall, and mercury vapor is poisonous. A safer and more portable instrument for measuring pressure, called an aneroid barometer, consists of a partially evacuated metal chamber connected to a pointer. When atmospheric pressure increases, it compresses the chamber and the pointer moves in one direction. When pressure decreases, the chamber expands, directing the pointer the other way. Changing weather can also affect barometric pressure. On a stormy day at sea level, pressure may drop to 980 millibars, although barometric pressures below 900 millibars have been reported during some hurricanes. In contrast, during a period of clear, dry weather, a typical high-pressure reading may be 1025 millibars. These changes are discussed more in Chapter 19. Atmospheric temperature. The temperature of the atmosphere changes with altitude. The layer of air closest to Earth, the layer we live in, is the troposphere. Virtually all of the water vapor and clouds exist in this layer, and almost all weather occurs here. Earth's surface absorbs solar energy, and thus the surface of the planet is warm. But, as explained earlier, continents and oceans also radiate heat, and some of this energy is absorbed by the troposphere. Lower parts of the troposphere absorb most of the heat radiating from Earth's surface. In contrast, at higher elevations in the troposphere, the atmosphere is thinner and absorbs less energy. Consequently, temperature decreases with increased elevation in the troposphere. Mountaintops are generally colder than valley floors, and commercial jet airliners must heat their cabins once reaching cruising altitudes, which are generally between 10 and 11 kilometers elevation. The top part of the troposphere is the tropopause, which lies at an altitude of about 17 kilometers at the equator, although it is lower at the poles. The tropopause is the boundary between the troposphere and the stratosphere above. It is characterized by an abrupt cessation in the steady decline in temperature with altitude, because cold air from the upper troposphere is too dense to rise higher. As a result, little mixing of air molecules occurs across the tropopause. The tropopause forms the floor of the stratosphere, in which temperature remains constant to 35 kilometers and then increases with altitude until, at about 50 kilometers, it is as warm as air at the Earth's surface. Although the stratosphere is above elevations at which commercial airliners can fly, many military jets can reach it if they really try. The stratosphere is not too high to become polluted by radioactive elements from atmospheric tests of atomic and hydrogen bombs. Large levels of anthropogenic radionuclides were released into the atmosphere during atmospheric tests of nuclear weapons conducted mostly in the 1950s and 1960s by the United States and former Soviet Union, and in the 1970s by France and China. Most of the radioactive debris from atmospheric test of hydrogen bombs reached the stratosphere and accumulated there, forming a reservoir of radioactive radionuclides. For many years, global fallout of these radionuclides from the stratosphere downward through the troposphere to Earth's surface was observed during the late spring, when heating of the ground surface and lower troposphere formed rising hot air that broke through the tropopause and disrupted the lower stratosphere. This disruption caused cold, radionuclide-rich air from the lower stratosphere to rapidly descend, causing the nuclear fallout. Each spring beginning prior to the 1963 moratorium on atmospheric testing of nuclear weapon until the early 1990s, the annual rate of radionuclide fallout peaked, although the annual peak concentration fell through this period. Since the 1990s, the biggest fluctuations in the concentration of radionuclides in the troposphere are due mostly to their resuspension from contaminated soil. Thus, although the annual springtime radionuclide fallout event no longer is significant in terms of providing the source of radionuclides in the troposphere, the deposition of radioactive elements during those events and the physical reworking of those deposits today provide the main source of atmospheric radionuclides in the troposphere. The reversal in the temperature profile between the troposphere and the stratosphere occurs because the two atmospheric layers are heated by different mechanisms. As already explained, the troposphere is heated primarily from below, by Earth. The stratosphere, however, is heated primarily from above, by direct incoming solar radiation. Oxygen molecules in the stratosphere absorb energetic ultraviolet rays from the sun. The radiant energy breaks the oxygen molecules apart, releasing free oxygen atoms. These free oxygen atoms then recombine to form ozone. Ozone absorbs ultraviolet energy more efficiently than oxygen does, and the absorption of UV radiation by the ozone warms the upper stratosphere. Ultraviolet radiation is energetic enough to affect organisms. Small quantities give us a suntan, but large doses cause skin cancer and cataracts of the eye, inhibit the growth of many plants, and otherwise harm living tissue. The ozone in the upper atmosphere protects life on Earth by absorbing much of this high-energy radiation before it reaches Earth's surface. Ozone concentration declines in the upper portion of the stratosphere, and therefore at about 55 kilometers above Earth, temperature once more begins to fall rapidly with elevation. This boundary between rising and falling temperature is the stratopause, the ceiling of the stratosphere. The second zone of declining temperature in Earth's modern atmosphere is the mesosphere. Little radiation is absorbed in the mesosphere, and the thin air is extremely cold. The ceiling of the mesosphere is the mesopause. Starting at about 80 kilometers above Earth, the temperature again remains constant and then rises rapidly in the thermosphere. Here the atmosphere absorbs high-energy X-rays and ultraviolet radiation from the Sunday high-energy reactions strip electrons from atoms and molecules, producing ions. The temperature in the upper portion of the thermosphere is just below freezing, not extremely cold by surface standards. The uppermost layer of the atmosphere is the exosphere, a layer of very diffuse gas that overlies the thermosphere and thins upward into the vacuum of space. In the exosphere, gas molecules are gravitationally influenced by to the Earth, but the density of gas is too low for the individual molecules to collide with each other, as gas normally does at lower atmospheric levels. Instead of colliding with other molecules, gas molecules in the exosphere travel along ballistic trajectories similar to the arc of a thrown ball. As they are pulled by Earth's gravity, slower gas molecules arc back into the thermosphere while some of the faster-moving Molecules continue into outer space and are lost. Air. Pollution. Ever since the first cave dwellers huddled around a smoky fire, people have introduced impurities into the air. The total quantity of these impurities is minuscule compared with the great mass of our atmosphere and with the monumental changes that occurred during the evolution of the planet. Yet air pollution remains a significant health, ecological, and climatological problem for modern industrial society. In 1948, Donora was an industrial town with a population of about 14,000 located 50 kilometers south of Pittsburgh, Pennsylvania. One large factory in town manufactured structural steel and wire, and another produced zinc and sulfuric acid. During the last week of October 1948, dense fog settled over the town. But it was no ordinary fog. The moisture contained pollutants from the two factories. After 4 days, visibility became so poor that people could not see well enough to drive, even at noon with their headlights on. Gradually at first, and then in increasing numbers, residents sought medical attention for nausea, shortness of breath, and constrictions in the throat and chest. Within a week, 20 people had died and about half of the town was seriously ill. Other incidents similar to what happened in Donora occurred worldwide. In response to the growing problem, the United States enacted the Clean Air Act in 1963. As a result of the Clean Air Act and its amendments, total emissions of air pollutants have decreased and air quality across the country has improved. It is even more encouraging to note that this decrease in emissions has occurred at a time when population, energy consumption, vehicle miles traveled, and gross domestic product have increased dramatically. Donora-type incidents in the United States have not been repeated. Smog has decreased, and rain has become less acidic. Yet some people believe that we have not gone far enough and that air pollution regulations should be strengthened further. Sources and types of air pollution are listed in Figure 17.13 and discussed in the following section. Gases released when fossil fuels are burned. Coal is largely carbon, which, when burned completely, produces carbon dioxide. Petroleum is a mixture of hydrocarbons, compounds composed of carbon and hydrogen. When hydrocarbons burn completely, they produce carbon dioxide and water as the only combustion products. Neither is poisonous, but both are greenhouse gases. If fuels were composed purely of compounds of carbon and hydrogen, and if they always burned completely, air pollution from the burning of fossil fuels would pose little direct threat to our health. However, fossil fuels contain impurities, and combustion is usually incomplete. As a result, other products form, most of which are harmful. Products of incomplete combustion include hydrocarbons such as benzene and methane. Benzene is a carcinogen, and methane is another greenhouse gas. Incomplete combustion of fossil fuels releases many other pollutants, including carbon monoxide, which is colorless and odorless yet very toxic. Additional problems arise because coal and petroleum contain impurities that generate other kinds of pollution when they are burned. Small amounts of sulfur are present in coal and, to a lesser extent, in petroleum. When these fuels burn, the sulfur forms oxides, mainly sulfur dioxide and sulfur trioxide. High sulfur dioxide concentrations have been associated with major air pollution disasters of the type that occurred in Donora. Today, the primary global source of sulfur dioxide pollution is electricity generation by coal-fired power plants. Nitrogen, like sulfur, is common in living tissue and therefore is found in all fossil fuels. This nitrogen, together with a small amount of atmospheric nitrogen, reacts when coal or petroleum is burned. The products are mostly nitrogen oxide and nitrogen dioxide. Nitrogen dioxide is a reddish-brown gas with a strong odor. It contributes to the browning and odor of some polluted urban atmospheres. Automobile exhaust is the primary source of nitrogen oxide pollution. Acid rain, as explained earlier, sulfur and nitrogen oxides are released when coal and petroleum burn. These oxides are also released when metal ores are refined. In moist air, sulfur dioxide reacts to produce sulfuric acid and nitrogen oxides react to form nitric and nitrous acid. These strong atmospheric acids dissolve in water droplets and fall as acid precipitation, also called acid rain. Acidity is expressed on the pH scale. A solution with a pH of 7 is neutral, neither acidic nor basic. On a pH scale, numbers lower than 7 represent acidic solutions and numbers higher than 7 represent basic ones. For example, soapy water is basic and has a pH of about 10, whereas vinegar is an acid with a pH of 2. Rain reacts with carbon dioxide in the atmosphere to produce a weak acid. As a result, natural rainfall has a pH of about 5.7. However, in the bad old days, before the Clean Air Act was properly enforced, rain was much more acidic. A fog in Southern California in 1986 reached a pH of 1.7, which approaches the acidity of toilet bowl cleaners. Consequences of acid rain: sulfur and nitrogen oxides impair lung function, aggravating diseases such as asthma and emphysema. They also affect the heart and liver and have been shown to increase vulnerability to viral infections such as influenza. Acid rain corrodes metal and rock. Limestone and marble are especially susceptible because they dissolve rapidly in mild acid. In the United States, the cost of damage and deterioration to buildings and building materials caused by acid precipitation is estimated at several $billion per year. Figure 17.15a is a map of average pH for rainfall across the conterminous United States in 1992. The northeastern United States was particularly susceptible to acid rain because it was downwind from the interior Rust Belt, the large region of the northern interior United States in which large-scale industry had developed since the 19th century. More recently, a 2016 study involved the analysis of 27 sites in the northeastern United States and eastern Canada over a period ranging between 8 and 24 years. The results show that long-term increases in pH occurred in the O and B soil horizons at most sites, trends that the study's authors attributed to reversal of the effects of acid rain on North American soils. Smog and ozone in the troposphere. Imagine that your great-grandfather had entered the exciting new business of making moving pictures. Old-time many filmmakers left the polluted, overcast, industrial Northeast. Southern California, with its warm, sunny climate and little need for coal, was preferable. Thus, a district of Los Angeles called Hollywood became the center of the movie industry. Its population boomed, and after World War II, automobiles became about as numerous as people. Then the quality of the air deteriorated in a strange way. People noted 4 different kinds of changes. A brownish haze called smog settled over the city. People felt irritation in their eyes and throats. Vegetable crops became damaged, and the sidewalls of rubber tires developed cracks. In the 1950s, air pollution experts worked mostly in the industrialized cities of the East Coast and the Midwest. When they were called to diagnose the problem in Southern California, they looked for the sources of air pollution they knew well, especially sulfur dioxide. But the smog was nothing like the pollution they were familiar with. These researchers eventually learned that incompletely burned gasoline in automobile exhaust reacts with nitrogen oxides and atmospheric oxygen in the presence of sunlight to form ozone. The ozone then reacts further with automobile exhaust to form smog. As you learned in section on atmospheric temperature, ozone in the stratosphere absorbs ultraviolet radiation and protects life on Earth. Yet, excessive ozone in the air we breathe is harmful. Is ozone a pollutant to be eliminated, or a beneficial component of the atmosphere that we want to preserve? The answer is that it is both. Depending on where it is found, ozone in the troposphere reacts with automobile exhaust to produce smog, and therefore it is a pollutant. Ozone in the stratosphere is beneficial, and the destruction of the ozone layer there creates serious problems. Ozone irritates the respiratory system, causing loss of lung function and aggravating asthma in susceptible individuals. Ozone also increases susceptibility to heart disease and is a suspected carcinogen. High ozone concentrations slow the growth of plants, which is a particularly serious problem in the rich, agricultural areas of California. Ozone pollution ranks as the 33rd leading cause of human death. As of 2018, over 95% of Earth's human population lives with unsafe levels of air pollution, using air quality guidelines from the World Health Organization. Using population-adjusted measurements of ozone, with greater weight given to ozone concentrated in densely populated areas, the State of Global Air 2018 reported that global levels of ozone pollution increased between 1990 and 2016. Within the United States, ozone levels fell during the same period, as air pollution controls and fuel emission standards were implemented. Toxic volatiles recall from Chapter 15 that a volatile compound is one that evaporates readily and therefore easily escapes into the atmosphere. Whenever chemicals are manufactured or petroleum is refined, some volatile byproducts escape into the atmosphere. When metals are extracted from ores, gases such as sulfur dioxide are released. When pesticides are sprayed onto fields and orchards, some of the spray is carried off by the wind. When you paint your house, the volatile parts of the paint evaporate into the air. As a result of all these processes, tens of thousands of volatile compounds are present in polluted air. Some are harmless, others are poisonous, and many have not been studied. Consider the case of dioxin. Very little dioxin is intentionally manufactured. It is not an ingredient in any herbicide, pesticide, or other industrial formulation. You cannot buy dioxin at your local hardware store or pharmacy. Dioxin forms as an unwanted byproduct in the production of certain chemicals and when specific chemicals are burned. For example, in the United States today, garbage incineration is the most common source of dioxin. When a compound containing chlorine, such as the plastic polyvinyl chloride, is burned, some of the chlorine reacts with organic compounds to form dioxin. The dioxin then goes up the smokestack of the incinerator, diffuses into the air, and eventually falls to earth. Cattle eat grass lightly dusted with dioxin and store the dioxin in their fat. Humans ingest the compound mostly in meat and dairy products. The EPA estimates that the average U.S. citizen ingests about 0.0000000001 gram of dioxin in food every day. Although this is a minuscule amount, the EPA has argued that dioxin is the most toxic chemical known and that even these low background levels may cause adverse effects such as cancer, disruption of regulatory hormones, reproductive and immune system disorders, and birth defects. Others disagree. The Chemical Manufacturers Association has written, there is no direct evidence to show that any of the effects of dioxins occur in humans in everyday levels. A 2016 study published in the Journal of Epidemiology presented results from an 18-year-long study in which dioxin levels were measured from the milk of first-time Japanese mothers. The study showed that dioxin levels fell between 1998 and 2014 from 20.8 to 7.2 picograms of dioxin toxic equivalents in milk fat, despite a trend toward Japanese women having children later in life during this study period. Because dioxin accumulates in humans through time, milk from older mothers has higher dioxin levels. Thus, the lower overall dioxin levels over the course of the study suggests that concentrations in Japanese first-time mothers fell over the study period. No one knows whether very small doses of potent poisons ingested over long periods of time are harmful. Environmentalists argue that it is better to be safe than sorry, and that therefore we should reduce ambient concentrations of volatiles such as dioxin. This argument has helped spur the movement toward increased recycling and decreasing incineration of waste plastic as a means of disposal. Others counter that because the harmful effects of compounds like dioxin are unproven, we should not burden our economy with the costs of control. Particulates and aerosols. A particle, or particulate, is any small piece of solid matter, such as dust or soot. An aerosol is any small particle that is larger than a molecule and suspended in air. In the context of air pollution, all three terms are used interchangeably. Many natural processes release aerosols. Wind-blown silt, pollen, volcanic ash, salt spray from the oceans, and smoke and soot from wildfires are all aerosols. Industrial emissions add to these natural sources. Smoke and soot are carcinogenic aerosols formed whenever fuels are burned. Coal always contains clay and other non-combustible minerals that have accumulated along with the organic matter in the depositional environment in which the coal formed, commonly a swamp. When the coal burns, some of these minerals escape from the chimney as fly ash, which settles as gritty dust. When metals are mined, the drilling, blasting, and digging raise dust, and this too adds to the total load of aerosols. In 1988, EPA epidemiologists noted that whenever atmospheric aerosol levels rose above a critical level in Steubenville, Ohio, the number of fatalities from all causes, car accidents to heart attacks, rose. After several studies substantiated the Steubenville report, the EPA proposed additional reductions of ambient aerosol levels in the United States. Opponents argued that it is unfair to target all aerosols because the term covers a wide range of substances from a benign grain of salt to a deadly mist of toxic volatiles. Depletion of the ozone layer as described in section on atmospheric temperature. Solar energy breaks apart oxygen molecules in the stratosphere, releasing free oxygen atoms. The free oxygen atoms combine with oxygen molecules to form ozone. Ozone absorbs high-energy ultraviolet light. This absorption protects life on Earth because ultraviolet light causes skin cancer, inhibits plant growth, and otherwise harms living tissue. In the 1970s, scientists learned that organic compounds containing chlorine and fluorine, called chlorofluorocarbons, and compounds containing bromine and chlorine, called halons, rise into the upper atmosphere, react with, and destroy ozone. CFCs have no natural source, but were entirely synthesized for such diverse uses that included cooling agents in almost all refrigerators and air conditioners, propellants in aerosol cans, and as an expanding agent in styrofoam coffee cups and some polystyrene building insulation. Manufactured before the mid-1980s. In 1985, scientists observed an unusually low ozone concentration in the stratosphere over Antarctica, a phenomenon called the ozone hole. Since it was discovered, the low concentration of ozone over Antarctica declined further until, by 1993, it was 65% below normal over 23 million square kilometers, an area almost the size of North America. Research groups also reported significant increases in ultraviolet radiation from the sun at ground level in the region. In addition, scientists recorded ozone depletion in the northern hemisphere. In March 1995, ozone concentration above the United States was 15 to 20% lower than during March 1979. Data on global ozone depletion persuaded the industrial nations of the world to limit the use of CFCs and other ozone-destroying compounds. In a series of international agreements signed between 1978 and 1992, many nations of the world agreed to reduce or curtail production of compounds that destroy atmospheric ozone. Most industrialized countries stopped production of CFCs on January 1, 1996. The international bans have had positive results. The concentration of ozone-destroying chemicals peaked in the troposphere in 1994 and has been declining ever since. Although CFCs are projected to remain in the atmosphere for over 100 years. The CFCs and halons already in the atmosphere break down slowly, but at least the measured concentrations of these ozone-destroying chemicals are declining. In a review article published in May 2006, the authors concluded that ozone abundances have at least not decreased. For most of the world, although natural cycles make it difficult to judge the relative effects of human and natural influences. In summary, they write, it is therefore unlikely that ozone will stabilize at levels observed before 1980, when a decline in ozone concentrations was first observed. As of 2016, 11 different CFC compounds known to be completely synthetic still occur in Earth's atmosphere. Chapter 18, Energy Balance in the Atmosphere. Introduction. Weather is the state of the atmosphere at a given place and time. Temperature, wind, cloudiness, humidity, and precipitation are all components of weather. The weather changes frequently, from day to day or even from hour to hour. Climate is the characteristic weather of a region, particularly the temperature and precipitation, averaged over several decades. Miami and Los Angeles have warm climates, summers are hot and even the winters are warm. In contrast, New York and Chicago experience much greater temperature extremes. Even though winters are cool and often snowy, summers can be almost as hot as those in Miami. Seattle experiences moderate temperatures with foggy, cloudy winters. In this and the following 2 chapters, we discuss the atmosphere, weather, and climate. In Chapter 21, we will consider global climate change. Many of the processes that drive energy balance in the atmosphere vary in gradual and predictable manners. But the weather and climate don't always vary gradually and predictably because they are affected by many complex, overlapping system interactions, and by threshold and feedback mechanisms. As a simple example, incoming solar radiation is most intense at the equator and decreases predictably toward the poles. But some high-latitude locations are warmer than regions closer to the equator, and on any given day, it can be warmer in Montreal than in Houston. In this and subsequent chapters, we will explain the fundamental processes that drive weather and climate, and how they interact. Incoming solar radiation. Solar energy streams from the sun in all directions, and Earth receives only 1/2 of the total solar output. However, even this tiny fraction warms Earth's surface and makes it habitable. The space between Earth and the sun is nearly empty. How does sunlight travel through a vacuum? In the late 1600s and early 1700s, light was poorly understood. Isaac Newton postulated that light consists of streams of particles that he called packets of light. Two other physicists, Robert Hooke and Christian Huygens, argued that light travels in waves. Today we know that Hooke and Huygens were correct. Light behaves as a wave, but Newton was also right. Light acts as if it is composed of particles. But how can light be both a wave and a particle at the same time? In a sense, this is an unfair question because light is fundamentally different from familiar objects. Light is unique, it behaves as a wave and a particle simultaneously. Particles of light are called photons. In a vacuum, photons travel only at one speed, the speed of light, never faster and never slower. The speed of light is 310 meters per second. At that rate, a photon covers the 150 million kilometers between the Sun and Earth in about 8 minutes. Photons are unlike ordinary matter in that they appear when they are emitted and disappear when they are absorbed. Light also behaves as an electrical and magnetic wave, called electromagnetic radiation. Terminology describing a light wave is the same as for sound waves or ocean waves. Its wavelength is the distance between successive wave crests. The frequency of a wave is the number of complete wave cycles, from crest to crest, that pass by any point in a second. Electromagnetic radiation occurs in a wide range of wavelengths and frequencies. The electromagnetic spectrum is the continuum of radiation of different wavelengths and frequencies. At one end of the spectrum, radiation given off by ordinary household current has a long wavelength and low frequency. At the other end, cosmic rays from outer space have a short wavelength and very high frequency. Visible light is only a tiny portion of the electromagnetic spectrum. Absorption and emission. If you go outside on a cold, snowy, February day, you wear a heavy jacket, hat, and gloves. Yet the sunlight warms your face. If the sky is clear, even though the temperature may be well below freezing, you must wear sunglasses to prevent snow blindness, and if you have unprotected fair skin, you will suffer sunburn. Each photon is a tiny packet of concentrated energy. The energy of a single photon is related only to the frequency of the light, and not to the ambient temperature. When a photon strikes your face, it may be absorbed. During absorption of radiation, the energy of the photon may initiate chemical and physical reactions in the molecules of your skin. One possible reaction is roughly analogous to cooking, and this reaction causes sunburn or tan. A photon may also cook a molecule in the retina of your eye, and if this reaction occurs frequently enough, you will become snow blind. Some absorbed photons do not cause chemical reactions, instead they cause molecules to vibrate or rotate more rapidly. This rapid motion makes your skin feel warm. Alternatively, a photon's energy may be transferred to an electron in a molecule. In this case, the electron jumps to what scientists call an excited state. It has a higher level of energy than its ground state. But electrons do not remain in their excited states forever. Frequently they fall back to a lower energy state, initiating emission of radiation in the process. In other words, the photon's energy was transferred to the electron and eventually the electron releases that energy back in the form of a photon. All objects emit radiant energy at some wavelength. Let's shift our focus from your skin to an iron bar. An iron bar at room temperature emits infrared radiation. This radiation has low energy and long wavelengths. It is invisible because the energy is too low to activate the sensors in our eyes. Infrared radiation is sometimes called radiant heat, or heat rays. Thus, even at room temperature, an iron bar radiates heat. If you place the bar in a hot flame, it begins to glow with a dull, red color when it becomes hot enough. The heat has excited electrons in the iron bar, and the excited electrons then emit visible, red, electromagnetic radiation. If you heat the bar further, it gradually changes color until it becomes white. This demonstration shows another property of emitted electromagnetic radiation. The wavelength of the radiation is determined by the temperature of the source. With increasing temperature, the energy level of the radiation increases, the wavelength decreases, and the color changes progressively. The sun's surface temperature is about 6,000 degrees Celsius. Because of its high temperature, the sun emits relatively high energy radiation, primarily in the ultraviolet and visible portions of the spectrum. When this radiation strikes Earth, it is absorbed by rock and soil. After the radiant energy is absorbed, the rock and soil re-emit it. But Earth's surface is much cooler than the Sun's. Therefore, Earth emits low-energy, infrared heat radiation, which has a relatively long wavelength and low frequency. Thus, Earth absorbs high-energy, visible light and emits low-energy, invisible, infrared heat radiation. Reflection radiation reflects from many surfaces. We are familiar with the images reflected by a mirror or the surface of a still lake. Some surfaces are better reflectors than others. The reflectivity of a surface is referred to as its albedo and is often expressed as a percentage. A mirror reflects nearly 100% of the light that strikes it and has an albedo close to 100%. Even some dull-looking objects are efficient reflectors. Light is bouncing back to your eye from the white paper of this page, although very little is reflected from the black letters. Snowfields and glaciers have high albedos and reflect 80 to 90% of sunlight. Clouds have the second highest albedo and reflect 50 to 55% of sunlight. On the other hand, city buildings and dark pavement have albedos of only 10 to 15%. Forests, with many independent surfaces of dark leaves, have an even lower albedo of about 5%. The oceans, which cover about 2/3 of Earth's surface, also have a low albedo. As a result, they absorb considerable solar energy and strongly affect Earth's radiation balance. Thus, the temperature balance of the atmosphere is profoundly affected by the albedos of the hydrosphere, geosphere, and biosphere. If Earth's albedo were to rise by growth of glaciers or cloud cover, the surface of our planet would cool. Alternatively, a decrease in albedo would cause warming. Thus, the growth and shrinking of Earth's snow and ice is a classic example of a feedback mechanism. If Earth were to cool by a small amount, snowfields and glaciers would grow. But snow and ice reflect solar radiation back into space and lead to additional cooling, which causes further expansion of the snow and ice, and so on. Scattering. On a clear day, the sun shines directly through windows on the south side of a building, but if you look through a north-facing window, you cannot see the sun. Even so, light enters through the window, and the sky outside is blue. If sunlight were only transmitted directly, a room with north-facing windows would be dark and the sky outside the window would be black. Atmospheric gases, water droplets, and dust particles scatter sunlight in all directions, as shown in Figure 18.5. It is this scattered light that illuminates a room with north-facing windows and turns the sky blue. The amount of scattering is inversely proportional to the wavelength of light. Short wavelength blue light, therefore, scatters more than longer wavelength red light. The sun emits light of all wavelengths, which combine to make up white light. Consequently, in space the sun appears white. The sky appears blue from Earth's surface because the blue component of sunlight scatters more than other frequencies and colors the atmosphere. The sun appears yellow from Earth because yellow is the color of white light with most of the blue light removed. The radiation balance. With this background, let us examine the fate of sunlight as it reaches Earth. Of all the sunlight that reaches Earth, 50% is absorbed, scattered, or reflected by clouds and atmosphere, 3% is reflected by Earth's surface, and 47% is absorbed by Earth's surface. The absorbed radiation warms rocks, soil, and water. If Earth absorbs radiant energy from the sun, why doesn't Earth's surface get hotter and hotter until the oceans boil and the rocks melt? The answer is that rocks, soil, and water re-emit virtually all the energy they absorb. As explained previously, most solar energy that reaches Earth is short wavelength, visible, and ultraviolet radiation. Earth's surface absorbs this radiation and then re-emits the energy mostly as long wavelength, invisible, infrared radiation. Some of this infrared heat escapes directly into space, but some is absorbed by the atmosphere. The atmosphere traps this heat radiating from Earth and acts as an insulating blanket. If Earth had no atmosphere, radiant heat loss would be so rapid that Earth's surface would cool drastically at night. Earth remains warm at night because the atmosphere absorbs and retains much of the radiation emitted by the ground. If the atmosphere were to absorb even more of the long-wavelength radiant heat from Earth, the atmosphere and Earth's surface would become warmer. This warming process is called the greenhouse effect. Some gases in the atmosphere absorb infrared radiation and others do not. Oxygen and nitrogen, which together make up almost 99% of dry air at ground level, do not absorb infrared radiation. Water, carbon dioxide, methane, and a few other gases do. Thus, they are called greenhouse gases. Water is the most abundant and most powerful greenhouse gas in Earth's atmosphere, and for 50 to 75% of the greenhouse effect today. The abundance of water vapor at the tropopause and in the lower stratosphere is particularly important because it determines how much energy escapes the atmosphere into outer space. Water passes from the troposphere across the tropopause to the lower stratosphere, mostly at the low-latitude tropics, where hot, wet air wells upward through the troposphere and beyond into the stratosphere. In addition to water, the upwelling also carries hydrogen and methane across the tropopause and into the lower stratosphere, where they react to form more water. Once in the stratosphere, the water moves to higher latitudes and eventually downwells back into the troposphere. This circulation of water back and forth across the tropopause is called Brewer-Dobson circulation. Stratospheric water is important because under the bombardment of radiation from the sun, water in the stratosphere breaks down, releasing O molecules that destroy ozone. In addition, the O molecules react with gases containing Cl to produce compounds that also destroy ozone. Thus, in addition to being a major contributor to global warming as a greenhouse gas, water in the stratosphere contributes to ozone loss, which allows more harmful radiation to reach the surface. One study published in Nature suggested that decreased concentrations of stratospheric water between 2000 and 2010 partially offset the global temperature increases caused by steadily increased concentrations of carbon dioxide during that time. The study also showed that relatively high levels of stratospheric water during the 1980s and 1990s likely accelerated global warming during those periods beyond that produced from increased carbon dioxide emissions alone. Carbon dioxide is an important greenhouse gas because its abundance in the atmosphere can vary as a result of several natural and industrial processes. Methane has become important because large quantities are released by industry and agriculture. The greenhouse effect and global climate change are discussed in more detail in Chapter 21. Dust, cloud cover, aerosols, and other particulate air pollutants also affect Earth's atmospheric temperature by altering the amount of sunlight that is absorbed or reflected. Large volcanic eruptions can inject enough ash and dust into the troposphere to partially block sunlight from reaching Earth, causing several years of global cooling as the dust settles. In addition, large volcanic eruptions in which ash clouds reach the tropopause can inject sulfur dioxide gas into the overlying stratosphere. Figure 18.9. Within about a month, the sulfur dioxide gas converts to tiny droplets of sulfuric acid about 1 micrometer in diameter. The droplets, called stratospheric aerosols, also reflect incoming solar radiation back into outer space, causing cooling. One 2011 study estimated that, between 2000 and 2010, stratospheric sulfur aerosols from volcanic eruptions offset the effects of caused global warming by roughly 1/3. The effect of human-caused pollution on global climate change is harder to interpret. Dust and aerosols close to the surface of Earth not only reflect incoming solar radiation but also absorb infrared radiation emitted by the ground. The net result depends on a complex balance of factors, including particle size, particle composition, and natural cloudiness. Whatever the outcome, it is certain that whenever people change the composition of air, they run the risk of altering weather and climate. Energy storage and transfer, the driving mechanisms for weather and climate, heat and temperature. All matter consists of atoms and molecules that are in constant motion. They fly through space, they rotate, and they vibrate. The temperature, or measure of heat in a substance, is proportional to the average speed of the atoms or molecules in a sample. In a teacup full of boiling water, the water molecules are racing around rapidly, smashing into each other, spinning like so many boomerangs, and vibrating like spheres connected by pulsating springs. In a bathtub full of ice water, the water molecules are also moving, but much more slowly. Molecules in the hot water are moving faster than those in the cold water, so the hot water has a higher temperature. In contrast, heat is a measure of the total energy in a sample. It is related to the average energy of every molecule multiplied by the total number of molecules. It may seem counterintuitive, but there is more heat in a bathtub full of ice water than in a teacup full of boiling water. The average molecule in the ice water is moving slower and therefore has less energy than the average molecule in the boiling water. But there are so many more molecules in the bathtub than in the teacup that the total heat energy is greater. Heat transport by conduction and convection. If you place metal frying pan on the stove, the handle gets hot, even though it is not in contact with the burner, because the metal conducts heat from the bottom of the pan to the handle. Conduction is the transport of heat by direct collisions among atoms or molecules. When the frying pan is heated from below, the metal atoms on the bottom of the pan move more rapidly. They then collide with their neighbors and transfer energy to them. Like a falling row of dominoes, energy is passed from one atom to another throughout the pan until the handle becomes hot. Metals conduct heat rapidly and efficiently, but air is a poor conductor. To understand how air transports heat, imagine that a heater is placed in one corner of a cold room. The heated air in the corner expands, becoming less dense. This light, hot air rises to the ceiling. It flows along the ceiling, cools, falls, and returns to the stove, where it is reheated. Recall from Chapter 6 that convection is the upward end. Downward flow of fluid material in response to heating and cooling. In addition to heat-driven movement of fluids through convection, movements of hot or cold fluids can be driven by processes other than heating and/or cooling and resulting changes in density. For example, the Gulf Stream moves heat horizontally from the Caribbean region northward to the coast of Western Europe, which is warmed by the current. Such lateral movement of heat is called advection. Although advection is commonly confused with convection because both involve moving fluids that carry heat, it is the heat itself that drives convection, whereas advection involves a fluid that is moving for some other reason and that carries heat from one place to another in the process. For example, in a forced air furnace, air heated by the furnace is advected into the living space by a fan and series of ducts. Both advection and convection also occur in the atmosphere. If air in one region is heated above the temperature of surrounding air, this warm air becomes less dense and rises, or convects, just like a hot air balloon. Eventually, the warm air moves laterally, causing advection of the heat as the air mass moves from one location to another. Similarly, cool, dense air from another part of the atmosphere might sink or convect downward. As it does so, it will displace other air laterally, and this air will advect whatever heat it has with it as it moves. In common speech, this horizontal airflow is called wind. Changes of state given the proper temperature and pressure. Most substances can exist in three states: solid, liquid, and gas. However, at Earth's surface, many substances commonly exist in only one state. In our experience, rock is almost always solid and molecular oxygen is almost always a gas. Water commonly exists in all three states, as solid ice, as liquid, and as gaseous water vapor. Latent heat is the energy released or absorbed when a substance changes from one state to another. As shown in Figure 18. 12, about 80 calories are required to melt a gram of ice at a constant temperature of 0 degrees Celsius. Another 540 to 600 calories are needed to evaporate a gram of water at constant temperature and pressure. The energy transfers also work in reverse. When 1 gram of water vapor condenses to liquid, 540 to 600 calories are released. When 1 gram of water freezes, 80 calories are released. Sublimation is the transformation directly from solid ice to water vapor, without passing through an intermediate, the liquid phase. For water, this process requires about 620 calories per gram. If you walk onto the beach after swimming, you feel cool, even on a hot day. Your skin temperature drops because water on your body is evaporating, and evaporation absorbs heat, cooling your skin. Similarly, evaporation from any body of water cools the water and the air around it. Conversely, condensation releases heat. The energy released when water condenses into rain during a single hurricane can be as great as the energy released by several atomic bombs. The energy absorbed and released during freezing, melting, evaporation, and condensation of water is important in the atmospheric energy balance. For example, in the northern latitudes, March is usually colder than September, even though equal amounts of sunlight are received in both months. However, in March much of the solar energy is absorbed by melting snow. Snow also has a high albedo and reflects sunlight efficiently. Evaporation cools seacoasts, and the energy of a hurricane comes, in part, from the condensation of massive amounts of water vapor. Heat storage: if you place a pan of water and a rock outside. On a hot summer day, the rock becomes hotter than the water. Both have received identical quantities of solar radiation. Why is the rock hotter? One specific heat is the amount of energy needed to raise the temperature of 1 gram of material by 1 degree Celsius. Specific heat is different for every substance. Water has an unusually high specific heat. The amount of energy needed to raise 1 cubic centimeter of water by 1 degree Celsius is 1 calorie. In contrast, the specific heat of basalt is only about 1/5 that of water, so only about 20% of the heat required to heat water by 1 degree Celsius is needed to heat the same volume of basalt by 1 degree Celsius. Thus, if water and rock absorb equal amounts of energy, the rock becomes hotter than the water. 2. Rock absorbs heat only at its surface, and the heat travels slowly through the rock. As a result, heat concentrates at the surface. Heat disperses more effectively through water for 2 reasons. First, solar radiation penetrates several meters below the surface of the water, warming it to this depth. Second, water is a fluid